All right, so we want to look at the last new topic that will cover this term, and it's known as Cauchy-Euler equation. So you may recognize the last name of Euler from geometry. He contributed a lot to geometry if you happen to be teaching high school geometry or working with students doing that. It looks like Euler, E-U-L-E-R, but it's pronounced Euler. And these equations, honestly, are probably the easiest ones that we'll talk about, so it's a good way to end. This particular family of equations are linear second-order differential equations. And so keep in mind what makes something be linear is that the independent variable, nothing funny is going on with that. And its derivatives, right? So I mention that because all of a sudden now I've got some t's and some t squares in there. But keep in mind, I'm looking for y or an f of t function. So my independent variable is f, or in this case y, y double prime, y prime, y prime. So that nothing is being squared, nothing else is going on with those. That's what makes it be linear. And it is second order because it's the second derivative. That is independent than the t squared and the t and so on. Okay? These are known as variable coefficient equations. Variable coefficient equations. And just like with the other things that we've solved, we have an associated characteristic equation that we want to look at. So I've got coefficients a, b, and c, or numerical coefficients rather, a, b, and c. I have a variable coefficient, of course, in front of that y double prime, a variable coefficient in front of this y prime, and so on. So my associated characteristic equation looks like this. AR squared plus B minus A R plus C. So here we go. Let's look at an example. And as in the past where we solved that characteristic equation, we're going to end up with three cases. So be anticipating those three cases each time. So number one, let's solve this problem. 3t squared y double prime plus 11t y minus 3y all equal to 0. So again, I know it's an Euler equation because it's got these variable pieces in front of it. It fits that form that we just talked about. Okay, so I want to write the associated characteristic equation. So that's going to be, if I think about this as A, B, and C, I have 3r squared plus B minus A, 11 minus 3, and then plus C, in this case C of course is negative. So my associated characteristic equation looks like 3r squared plus 8r minus 3. And just like with everything else, I want to factor that, or I want to solve it in some fashion. This particular problem, I think, factors into double check my arithmetic real quick, but I believe it's going to be 3r minus 1 and an r plus 3. So I get solutions for r of 1/3 and negative 3. And so remember, these are a different kind of equation. They've got variables in front. So my characteristic equation looks different. These are going to be in the form t to the 1/3, actually some constant, and t to the negative 3 for each of those two pieces. My characteristic solution then is c1t to the 1/3 plus c2t to the negative 3. So the only new thing that's changing is the characteristic equation, and then I'm not writing e to powers, or that form has changed. It's now t, a variable, to a power each time. Okay, so as always, we've got a couple of cases, and I think, you know, as far as the work here, I think you can get there without any problem. You'll have a few homework problems, but they'll be similar to these cases, and I'll certainly post solutions. So the first case is this one, where we have two distinct roots. And so they're always going to be in the form of t to the first root and t to the second root. Okay, so that's just a matter of writing down those solutions. That's the best case to be in. Alright, but you already know the other cases that can happen. So the second case is a repeating root. And for a repeating root, I'm going to have, just like I've been doing, t to some r power, just like we did in the previous example. And then I need to modify that second solution. And we're going to do the natural log of t to that r power. So again, the characteristic equation solution is the combination of each of these, a linear combination of each of those. Okay? And so then the third case that we encounter is an imaginary root. Remember, we get imaginary roots that kind of fit this form, a real and an imaginary part, an alpha and a beta. And so here I'm going to have some constant t to the alpha cosine of beta times the natural log of t, which is looks intimidating, but y'all, that's as bad as it gets. Plus some other constant. Well, let me back up. For y2, some other constant t to the alpha sine beta natural log t. And what I started writing was the solution to the characteristic equation, which we know to be the combination of those two things. So the only trick today is using this new characteristic equation. If it factors, great. If it factors and it's got a repeater, that's fine too. That's the easy cases. The only tricky case is the quadratic formula and getting this crazy form, but you have it in front of you. Okay? So I'm going to post a little bit of homework with that, and of course the solutions to those homework problems, and I'm going to go ahead and open your last test for you. So that test is really due during week 10, which is, I think week 9 is next week and week 10 is the next. But I'm going to go ahead and open it because this material is not difficult, and you might want to spend a little time with that. Again, 4 problems, basically one of each kind. General solutions to the homogeneous cases, basically those 3 situations. The method of undetermined coefficients, the method of variation of parameters, and now these Cauchy-Euler equations to solve. And it'll probably be just one of those situations, one of these 3 cases. Alright, as always, let me know if you have any questions.